All right, let's get started with 12.2. So we're going to learn some techniques for evaluating our limits. So up till now, we've just put them into our tables and checked on them. Now we're going to learn two distinct techniques to go along with that. All right, so one is the dividing out technique. So we notice here when we start, if we plug in -3, we're going to get -3 squared plus -3 minus 6, and in the denominator we're going to have -3 plus 3. That's not going to work out. So we could plug this into our y equals, go to our table, figure out what's going on. But if we factored the numerator and ended up with x plus 3 and x minus 2, the denominator is still x plus 3. If we can cancel those and then do the limit of x approaching -3, just do direct substitution into this after we've canceled out. What's -3 minus 2? -5. And that is going to be our limit. All right, so if you can cancel out, go ahead and do it. We're still not going to have a value at x equals -3 because it would be undefined. But we will be able to find the limit through direct substitution. All right, so use that direct substitution dividing out technique on number 11. All right, let's try one more time here. And just a reminder to factor by grouping here. Let's pull out an x. We're left with, an x squared. We're left with x minus 1 plus a 1. X minus 1. So we can rewrite this as x minus 1 over x squared plus 1. X minus 1. And there's our common term we can cancel. Let's direct substitute using 1. So we'll have 1 over x squared plus 1. Plug in 1 for x. 1 over 1 squared plus 1. And we get a half. So the limit as x approaches 1 is going to be 1/2. Try one more. Divide out and direct substitute for 15. All right, so we can also use a rationalizing technique. So you'll remember rationalize your denominator using conjugates. In this case, we're going to actually rationalize the numerator, and we'll get rid of the denominator. So what's the conjugate here? It's going to be the square root of x plus 1 plus 1. The key here, change that sign. All right, we need to do the same thing on the top and the bottom, numerator and denominator. Now the numerator is actually fairly straightforward because remember, a plus b times a minus b is equal to a squared minus b squared. So our a is the square root of x plus 1, so that just turns into x plus 1. And then minus 1 squared, which is just 1, all over. Let's leave this in parentheses. We don't need to distribute this. And the reason why here is that the 1 and the 1 cancel. The x's cancel. And we're left with 1 over the square root of x plus 1 plus 1. Let's use direct substitution, plugging in 0. 1 over the square root of 0 plus 1, that's just 1. Plus 1 is 2. The limit is going to be 1/2. All right, so rationalize, same steps, 25. All right, so example 4 says, you know what, sometimes neither of these are going to work, so we are going to have to go right back to our old tricks of using the table. So just a reminder, example 4 is what we did in 12.1 again. Let's go ahead and plug this in. 1 plus x to the 1 over x. And we'll go ahead and use a table close to 0, so -0.3, that's a good start. Let's go ahead and take a look. It looks like we're zooming in on something between 2.6 and 2.8. I'm going to change my table set actually and get a little closer and see if we can get a better idea here. So it looks like 2.71 maybe, 2.72 is what we're going for here. I'd call it 2.72. All right, so that'd be our answer for example 4. So use the old trick from 12.1, use your table, and get a limit for 37. All right, so same thing on 5. We've got our calculator, sin x over x. And just make sure that you are in radians for these. And this one says find your, approximate the limit graphically. So this one is just a reminder that yes, we can graph these things and trace in on 0. So I'm going to graph it, do a quick box zoom to see what's going on around x is 0. And when x is 0, hit the trace button. When x is close to 0, y is going to be close to 1. And we can see that by moving left and right. And what happens when x gets really close to 0. All right, so same steps here. See if you can do the same thing for sine of 2x over x. Be in radians. Okay, so now we're going to introduce this concept of one-sided limits. So we can just look at a limit coming from just the negative side, just from the left, or just from the positive side, just from the right. So let's find the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right for this problem here. So I'm going to go to the graphing calculator. We're going to plug this in. Absolute value is in math. Right there, of 2x divided by x. And I'm going to go to my table. I think we're at 0. Yes, we are. Okay. All right. From the left side, our y values are approaching -2. From the right side, it's approaching +2. So the way we would write this is the limit as x approaches 0 from the negative side of our function equals -2. The limit as x approaches 0 from the positive side of our function is +2. And since these things don't add up to the same thing, we just skip straight to this, we don't have a limit. And we know that already from 12.1. So only if the left and the right limits exist and are the same thing do we have a limit for the entire function. So go ahead and try 55 and see if you can find the limit by finding each of the one-sided limits, the left side and the right side. Okay, so let's look at these one-sided limits again. So piecewise function, we'll plug this in twice, 4 minus x. Actually, you know what? Let's just plug in 1. What's 4 minus 1? 4 minus 1 is 3. 4 times 1 minus 1 squared is also 3. So in this case, we're approaching the same number. We're approaching 3 from both sides. So our limit is going to be 3. We get the same thing from both sides. All right, go ahead and try 59. You can use direct substitution on this one as well. All right, same type of situation. What's the limit as x approaches 2? The limit as x approaches 2 from the left side is 20. The limit as x approaches 2 from the right side is 22. Are they the same? No, they're not. So we do not have a limit. The limit does not exist because we approach different values from the left and the right. Same type of problem on 81. Show that the limit does not exist. All right, let's finish up here with our old friend, the difference quotient. We're going to find the difference quotient here for the function of 3 plus h minus the function of 3 if the function is x squared minus 1. So 3 plus h squared minus 1 minus let's see, we're plugging in 3. 3 squared minus 1 all over h. We'll clean this up, and we've got 9 plus 6h plus h squared minus 1 minus 9 plus 1 all over h. Let's do some canceling. Get out of here. And get out of here. We've got 6h plus h squared all over h. And we're trying to find the limit as h approaches 0. So we can't plug it in right away because we have h in the denominator and 0 can't be the denominator. But we can use that first technique we learned in this chapter, the dividing out technique. If we cancel our h's, what's the limit as h approaches 0 of 6 plus h? That's just going to be through direct substitution, 6 plus 0, or 6. All right? So tangle with direct substitution and the difference quotient here on 75, and you're all done for 12-2.